going to be going over day 3 from the Unit 10 note packet. The topic for today is piecewise limits and then also limits at infinity. We're going to begin with piecewise limits though. The directions down here say piecewise functions. When evaluating limits given a piecewise, you have to make sure the limit approaches the same number for the left and from the right. So this is considered a piecewise function because there's more than one piece. There's 2 pieces. Now remember, for a limit to exist, it has to approach the same y value from the left and the right. I'm going to start this one by graphing it, but this is going to be the only problem that I graph. We're going to learn a different way to do it instead of graphing. And I'm going to put 0 on here because that seems like an important number based off of my restrictions. And then I'm going to graph the top piece, which just says x, and it says graph x when x is less than or equal to 0. So remember how we did this. We would put 0, and then we'd pick numbers that are smaller than 0, so maybe -1 and -2. And we would just plug it into this function right here. So if I put 0 in, I get 0. If I put -1 in, -1. And if I put -2 in, I get -2. So back over here on my graph, I'm just going to plot those points. I have 0, 0, which I'm allowed to put a closed circle because of the or equal to. -1, -1. -2, -2. And you should see that it's a straight line. This is linear. This is just y equals x. And that's my first piece. My second piece I will do in blue. And I'm going to make an xy table. And I'm going to be using the bottom part of my piecewise function. This time it says use values for x is greater than 0. So even though it doesn't say or equal to 0, I'm going to put 0, 1, and 2. Those are numbers greater than 0, 1, and 2. And at 0, I'm going to put a little open circle there so that I remember when I go to graph it that it's going to be an open circle there. I'm going to take 0 and I'm going to plug it into this function. So 0 squared is 0. 1 squared is 1, and if I put 2 in here, 2 squared is 4. So if I was going to graph this, I'd make sure that my y values went up to 4, and I have 0, 0, which is an open circle. Now keep in mind that red dot closed it in. 1, 1, 2, 4, and the shape of this thing is a parabola, and it looks like this. So if I had this graph, and the question was, what is the limit as x approaches 0 of this function, I would look at my graph and I would make sure that as I came in from the left and as I came in from the right, that my y values are meeting. So coming from the left and the right as I get close to 0, the y values are meeting. And the y value right there is 0. So my answer to the limit is 0. That's how I can do it graphically. This one wasn't that difficult to graph, but some of the other ones are going to be more difficult to graph. So we're going to learn a different way to do it besides graphing. On number 2, the question's asking, find the limit as x approaches 1 of f of x. And I'm not going to graph it. What I'm going to do is I'm going to make sure that my coming from the left, I get an answer. And coming from the right, I get an answer, and I need to make sure that those answers are the same. So here's how I do it notation-wise. I'm going to say the limit as x approaches 1 from the left by putting a little minus sign there. And then I'm going to find the limit as x approaches 1 from the right. I have to make sure that I show both sides. And then I have to see which function should I use, top or bottom, when I'm coming from the left. Think about coming from the left. Those are numbers that are smaller than 1. Well, this top equation says use this when x is less than or equal to 1. That would be numbers that are smaller than 1. So I'm going to use the function x squared plus 1. That's my top function, or the function on the left. Make sure notation-wise that you're writing it there. Don't start plugging in yet. And now I'm going to say equals, and I'm going to just plug in the number 1 in for x, 1 squared plus 1, and I get 2. My left-hand limit's 2. Let's try the right-hand limit. So for the right, I'm going to be using this bottom function. It says use the bottom when x is greater than 1. That means coming from the right. So the bottom function was 2x. Please make sure you write the function right there. And then I'm going to substitute 1 in for x. And I get 2. Now I'm going to compare my left-hand limit and my right-hand limit. I got the same number for both. And so therefore, I can say that the answer to my problem, the actual limit, is 2. Okay. If I got different numbers, I would say does not exist, or DNE. Let's try number 3. Number 3 is a piecewise function again, and we're trying to find the limit as x approaches 3. And 3 is where we split on the piecewise. So the way that I do it, always use good notation, please. Lim as x approaches 3 with a little minus sign, and lim as x approaches 3 with a little plus sign. That means from the left and from the right. So from the left, I want to use the function that has values smaller than 3. That would be this top one. The top one says x is less than 3. I'm going to use this top equation. 2x plus 4. Make sure you're writing that in, not just substituting in yet. Now I'm going to substitute 3 in. So 2 times 3 plus 4. And I get 6 plus 4, which is 10. Let's look at the right-hand limit. From the right side, I'm going to use when x is greater than 3. So this bottom function, 3x minus 1. If I put 3 in, 3 times 3 minus 1. Well, 3 times 3 is 9, and 9 minus 1 is 8. And so this time, I'm comparing, just like before, but this time I get a different value from the left and the right. And so when that happens, the answer to my problem, to the actual limit, in fact, I'll write it down here since I'm squished up there, the limit as x approaches 3 of f of x equals, it doesn't work. So what we say is DNE, does not exist. That meant coming from the right, we were up at 10. Coming from the left, we were down at 8, and they did not meet. Okay, let's give 4 a try. So in problem 4, we're going to be finding the limit as x approaches 2. So lim as x approaches 2 from the left, little minus sign. Lim as x approaches 2 from the right, a little plus sign. Ooh, actually, I jumped ahead. This time, it doesn't say less than or greater than. Did you notice that? This one looks a little bit different. So we have to think about which one should we use for the limit. Now, a limit is as I come from the left and come from the right, what am I getting close to? I don't really care what happens at 2. So you never use the equal to. If you see the option of does not equal or equals, we're always going to use the function next to the does not equal for the limit. And I'll show you graphically in a moment what this is going to look like. My notation-wise, I don't need to show a left and a right. I can say the lim as x approaches 2, and I can write my function because we always recopy it. And that's the limit that I'm trying to find. Now, when I find this limit, if I were to just substitute in, I get 0 in the bottom, which is a problem. So because there's a problem, I have to resort to a different method. Hopefully you remember from last week, we can factor. The numerator is x plus 2, x minus 2. The denominator is x minus 2. I slash off my common factors, and I substitute in 2 plus 2, and I get 4. So my answer to this limit is actually 4. Okay, so if I'm given the choice of does not equals and equals, when I'm doing the limit, I always use the function next to the does not equal. If I was going to graph this one, just to kind of see what this thing looked like, because this one was a little bit different, I'm going to make a little mini graph down here because I ran out of space. And one thing I notice is that when x is 2, I do have a point. The point is 2 comma 5. So 1, 2, 3, 4, 5. 2 comma 5 is going to be a point. But then this right here is going to produce more than a point. This is going to produce some kind of other graph. Maybe it's curved, maybe it's a line. Let's see. To see, I would make a table, and it says x just cannot equal 2. So I'll pick some numbers that are smaller than 2. So maybe I'll pick 0 and 1. 2 won't work. And I'll pick some numbers that are bigger than 2, maybe 3 and 4. If I'm plugging these in fact, let me zoom in on this for you. If I'm plugging these into the circled graph, you might want to factor that circled graph before plugging in. Like this is x plus 2, x minus 2 over x minus 2. I can go ahead and slash those out just because it'll make it easier for me when I'm plugging in. So if I plug 0 into here, I have 0 plus 2, which is 2. If I put 1 in here, 1 plus 2 is 3. If I were to plug 2 in here, I know it's not going to work. In fact, what's going to happen at 2 is there's going to be a hole in my graph. But if I wanted to see like where that hole was, I could plug 2 into what's left. So 2 plus 2, or 4. So at 2 comma 4, there's a hole. If I put 3 in, 3 plus 2 is 5. If I put 4 in, 4 plus 2 is 6. And then if I came over here, this is going to be a linear function. I'm going to have 0 comma 2, 1 comma 3, 2 comma 4, I have an open circle, 3 comma 5, 4 comma 6. I have a graph that looks like this. And so I have a linear graph that has a hole in the middle of it, and then I've got this random dot on top of the hole. The random dot can never be the answer to a limit. The limit can only be coming from the left and coming from the right. What is that y value getting really close to? And that open circle is 4. So graphically, that's what that thing would look like. All right, let's take a look at number 5. Now, problem number 5, they're asking us to find the limit as x approaches 5. If I look at my piecewise, should we use the one next to the equals or the one next to the does not equal? And we always use the one next to the does not equal for a limit. So I can say the limit as x approaches 5. And I'm also realizing that this right here can factor. And when you're finding a limit, you're allowed to factor. That's one of our methods. So I'm going to go ahead and just jump right in and start factoring. The top factors into x minus 5 and x plus 4. I see a common factor, slash them out. That means there's a hole, but that's okay. A hole can be the answer to a limit. And now I'm going to plug in. I'm going to plug 5 back in for x. 5 plus 4, and I get that my answer is 9. All right, our last piecewise one is number 6. And if I look at problem number 6, I notice the way that it's defined is using a less than and a greater than symbol. So kind of like our first ones. Let me zoom in on this. And we're going to have to show from the left and from the right. So use good notation, and let's go ahead and write the lim as x approaches 1 from the left, the lim as x approaches 1 from the right, and let's figure out which functions we're supposed to use. From the left, I need to use numbers that are smaller than 1 or less than 1. So I'm using the top function, x squared plus 7. I'll go in and put in 1. 1 squared plus 7 is 8. Now let's find the right-hand limit. So the right-hand limit, I'm going to use the bottom piece because it says when x is greater than 1. That would be to the right of 1. I'm going to use 3x. 3 times 1, or 3. So what do we think? What do we think the answer is going to be? I'm supposed to compare my left-hand limit and my right-hand limit, and they are not the same number. And so if they are not the same number, I say that my limit, the limit, does not exist. DNE. Okay, if you flip your paper over, go to the next page. The next page talks about limits at infinity. Okay, limits as x approaches infinity. So we would recognize this type because the problem would say x approaches infinity, or it even might say x approaches negative infinity, okay? But what we have to look at when x approaches infinity, typically we will be given a rational function. That means a ratio or a fraction. And to decide what the answer is, these ones actually should be really quick. You have to look at the degree of the numerator and the denominator. The degree is the highest exponent. So if the numerator is less than the denominator, I'm talking about the degree, then the answer to the limit is 0. So for this example over here, I would look at this problem and compare the degrees. The degree of the numerator, the highest exponent, is 1. The denominator is 2. So when I compare, the numerator is smaller. Numerator is less than. The answer is always 0. So my answer is 0. Here, it works the same exact way as if x is going to negative infinity. I'm using the same rule. The degree of the top is 1. The bottom is 2. The numerator's smaller. It's always going to be 0. So if you ever see that numerator smaller, the answer is 0. The other type, second type, is if the degree of the numerator is greater than, the degree of the denominator. So this time I would look over here and say, okay, the top is 3, the degree of the bottom's 1, so the numerator's bigger. If the numerator is bigger, it does not exist. And for this one, when I try to remember the different rules, I always think to myself, it's top heavy, the top is too big, it falls off, it doesn't work. If the top is bigger, it doesn't exist. Okay, and so this one right here, top is bigger, I would say D and E. Same thing when x goes to negative infinity. I still look at these guys. The top is bigger, D and E. Let's look at the third case. The third case that we hadn't discussed is if the degree of the numerator equals the degree of the denominator. And when that happens, you're going to have a value. Your answer is going to be the leading coefficient over the leading coefficient. So let's see what that would look like. Over here in my example, I noticed the degree of the numerator is 2 and the degree of the denominator is 2. So they're the same. So my answer is going to be the leading coefficient of the numerator over the leading coefficient of the denominator, or just 3. And the same exact rule holds if it's going to negative infinity. I'd look at the degree of the numerator, degree of the denominator are both 2, leading coefficient over leading coefficient. My answer is 3. These rules might seem familiar to you. Hopefully they do seem familiar to you. They are the same rules when we found horizontal asymptotes back a couple units ago. Okay, and the reason that they're the same rules is if you have a graph that has a horizontal asymptote, and I ask you, what is the limit as x goes to infinity all the way out here on the right? Remember, a horizontal asymptote, your graph gets really, really close to out on the right. So as the x's go to infinity, your horizontal asymptote is going to be the answer to your limit. So let's try these. We've got 10 problems to go through. Problem number 1. I notice immediately that it says, well, all of these say either they're going to infinity or negative infinity. So I have to look at the degree of the numerator and the degree of the denominator. Numerator's bigger. So it's top heavy, I think. Does not exist. D and E. Let's try number 2. Number 2, I'm looking at the degree of the numerator's 1, the degree of the denominator's 2. So this time the top is smaller. Whenever the top is smaller, it's 0. Okay, number 3. Degree of the numerator's 1, degree of the denominator's 1. So I notice they have the same degree. When it's the same degree, it's the leading coefficient, which was 1 of the numerator, and the leading coefficient of the denominator, which is also 1. So I get an answer of 1. Now, in number 4 is a little bit tricky because I see a square root, and we're supposed to be looking for the degree of the numerator and denominator. What I would do is look at just this highest term, the term with the highest exponent up top, and imagine taking the square root of that because it's underneath the square root. Well, the square root of 4 is 2, and the square root of x squared is just x. And so that's what I think about. I think about the top. I'm not so worried about this +1. It's not going to have a big effect on my graph. I'm going to look at the degree of the top now and the degree of the bottom now. And my degrees are the same. So it's going to be leading coefficient over leading coefficient, which is just 2. Okay, next up, number 5. Looking at my degrees, the degree of the top is 3, the bottom is 2. The numerator's larger, it's top heavy. It does not exist. Number 6. Ooh, number 6, I don't see a fraction here. If you don't see a fraction and you wanted to put in infinity, see what would happen here. You can put it over 1 if you want to, just so that you can compare. The degree of the numerator is 3. The denominator, there's no x there. If you had to put in x there so that you could see a degree, it would actually be x to the 0 power, because that's just 1. And so the degree of the denominator is 0. So in this case, the numerator is larger. I say DNE. Number 7, be very careful with number 7. Compare those degrees. 2, 2. So hopefully we saw that, and we saw that they were the same. So it's supposed to be leading coefficient over leading coefficient. The numerator's 2, but hopefully you saw this negative sign hanging out here. So the degree of the numerator is really -2. The denominator's 1. And so my answer is -2. Now you might ask, how did I know that the negative went with the numerator and not the denominator? It doesn't really matter. I could have put the negative with the numerator or the denominator, or just out front. Just don't put it with both, because then they'd cancel each other out. Okay, number 8. I see another problem that is not a fraction, so I would put it over top of 1, just like I did the one above it. My degree is 4. My denominator degree is 0. And so the degree of the numerator is larger. It's top heavy. It does not exist. Number 9. Number 9. I'm looking for the degree of the numerator. There's no x. So let's think about what we did over here when there was no x. If I had to put an x in, I'd have to make it x to the 0 power. And now I'm comparing. The degree of the numerator is 0, degree of the denominator is 2, and so the numerator is smaller. My answer is going to be 0. We have one last problem, number 10, and you might say, why is number 10 a challenge? It looks really similar to number 4, doesn't it? Let's compare number 10 and number 4. The problems look identical, except what x is approaching. Now, when something's under the square root or underneath a radical, that is the only time that the same thing is not going to happen when I'm going to positive infinity and negative infinity. So I am actually going to take the square root of this number, just like I did before. And the square root of 4x squared is 2x. But really, when I take something out of the square root, what I should technically have in front of it is a plus or minus. Like I have to decide which one to use. I should have done it up here, but we were on a roll and we hadn't talked about that yet. And so then I'd compare and I'd say, okay, degree of the numerator, degree of the denominator, they're the same. So my answer is going to be leading coefficient over leading coefficient. But should I use the +2 or the -2? And that's where this comes into play. If it's going to negative infinity, I'm going to use the -2. So I'm going to use -2 over 1, and that would be my answer. And I just want to throw my calculator under the screen for just a moment so that you can see what this thing would look like. All right, so what I have in here right now is the square root of 4x squared plus 1 divided by x. And I'm going to hit graph, and I'm going to look at what's happening as x goes to negative infinity, and then also what was happening back up here in number 4 as x went to positive infinity. So I'm going to hit graph, and my graph looks like this. Okay, it looks like I actually have two horizontal asymptotes. as x goes to positive infinity, so that's out here. I'm actually going to trace my graph. This is a dry erase, don't worry. As x goes to positive infinity out there, my y value is up at 2. But over here on the left, as x goes to negative infinity, my y value is down at negative 2. And what caused that to happen was the fact that my original equation had a square root in it. So if you ever come across a limit that has a square root in it, pay attention to whether the limit's going to positive infinity or negative infinity. Okay, that's it for our notes, but for this week, your assignment is different. Your assignment for the week is going to be doing a 20-question worksheet that's posted up on Google Classroom, and then to get credit for it, you're going to have to fill in the Google form. You'll just put your answers in. Something important I want to say about the Google form, and it does say that in there, but if the function does not exist, or if the limit does not exist, please write DNE with nice capital letters so that the Google form can accept your answer. All right, that is all.